7 planets orbit a star 40 light-years away. Not scattered randomly like our solar system, but compressed into a space smaller than Mercury's orbit around our Sun. If you stood on one of these worlds and looked up, neighboring planets would appear larger in the sky than our Moon. This isn't science fiction. This is TRAPPIST-1. In 2017, NASA announced the discovery of 7 Earth-sized planets around a single star. 3 of them sit in the habitable zone where liquid water could exist. Within weeks, TRAPPIST-1 became the most studied planetary system beyond our own. Scientists redirected telescopes, reprioritized missions, and rewrote research proposals. Because this system isn't just interesting, it's a laboratory for understanding whether life exists elsewhere in the universe. The star itself defies everything we assume about solar systems. TRAPPIST-1 is an ultra-cool dwarf star, barely larger than Jupiter, burning at temperatures that make it glow deep red rather than yellow like our Sun. It produces less energy in a year than our Sun emits in a day. Yet around this dim ember orbit 7 rocky worlds, each locked in gravitational resonance, their orbits synchronized like a cosmic clockwork mechanism that's been running for billions of years. Distance creates problems. 40 light-years means the light we see from TRAPPIST-1 today left that star before the internet existed. Any signal we send would take 40 years to arrive, and we'd wait another 40 for a response. Even our fastest spacecraft would need hundreds of thousands of years to reach it. This isn't a place we'll visit anytime soon. But distance doesn't mean irrelevance. The James Webb Space Telescope changed everything. For the first time in human history, we can analyze the atmospheres of planets orbiting other stars. We're not guessing anymore about what exists on distant worlds. We're measuring it directly. And TRAPPIST-1, with its compact system and frequent planetary transits, offers the best opportunity we have to detect signs of life beyond Earth. Here's what makes this system extraordinary. The planets don't just orbit randomly. They're locked in what astronomers call orbital resonance. For every 8 orbits TRAPPIST-1b completes, planets C, D, E, F, G, and H complete 5, 3, 2, 1, and 1 orbits respectively. This mathematical precision isn't coincidence. It's the signature of a system that has stabilized over billions of years, where gravitational interactions have pulled planets into synchronized motion. Think of it like pushing someone on a swing. Push at random times and nothing happens. Push at exactly the right moment in each cycle and the swing goes higher. The TRAPPIST-1 planets push and pull on each other at precisely the right times, stabilizing their orbits and potentially creating conditions that could support life. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 Earth days. It's too close to the star, receiving 4 times more radiation than Earth gets from the Sun. Surface temperatures likely exceed 400 degrees Fahrenheit. Any water that once existed has long since evaporated. But move outward and conditions change rapidly. TRAPPIST-1e sits in the middle of the habitable zone. It's almost exactly Earth's size, slightly more massive, with a density suggesting a rocky composition similar to our own planet. If water exists anywhere in this system, this is where we'd expect to find it. Scientists have focused enormous attention on this single world because it represents our best chance of finding life around an ultra-cool dwarf star. But there's a problem nobody expected. The first atmospheric measurements came back essentially blank. The James Webb Space Telescope detected no significant atmosphere on TRAPPIST-1b or C. For planets that should theoretically hold on to their atmospheres, this absence is troubling. It suggests something is stripping away these gaseous envelopes faster than planets can retain them. The star itself might be the culprit. Ultra-cool dwarf stars like TRAPPIST-1 are violent in ways our Sun isn't. They produce intense stellar flares, bursts of radiation and charged particles that slam into nearby planets. These flares can be thousands of times more powerful than solar flares. When they strike a planet, they don't just heat the surface. They strip away atmospheric particles, molecule by molecule, potentially rendering worlds uninhabitable despite being in the so-called habitable zone. This creates a paradox. Ultra-cool dwarf stars are the most common type of star in the galaxy. They make up roughly 75% of all stars. They also live for trillions of years, far longer than our Sun's projected 10 billion-year lifespan. If life needs time to develop, these stars offer more of it than any other stellar type. But if their flares destroy atmospheres, then the most common stars in the galaxy might also be the least likely to host life. Yet dismissing TRAPPIST-1 would be premature. Planets might protect themselves in ways we haven't considered. Strong magnetic fields could deflect stellar wind. Thick atmospheres could regenerate faster than flares strip them away. Oceans could provide a reservoir of gases that replenish atmospheric losses. And some planets in the system, particularly those farther from the star, might avoid the worst of the stellar violence while still receiving enough energy for liquid water. TRAPPIST-1F and G occupy positions at the outer edge of the habitable zone. They receive less radiation than Earth, but not so little that water must freeze. These worlds might be covered in ice with liquid oceans beneath frozen crusts, similar to Jupiter's moon Europa or Saturn's moon Enceladus. Such environments could be remarkably stable, shielded from stellar flares by kilometers of ice while maintaining liquid water in contact with rocky cores where chemical reactions could support life. The density measurements tell us something unexpected. These planets aren't identical copies of Earth. Their densities vary significantly, suggesting different compositions. Some might be water worlds with deep global oceans. Others could be desiccated rocks stripped bare by stellar radiation. A few might have retained thick atmospheres of hydrogen and helium. The system isn't uniform. It's diverse, offering multiple pathways for habitability or multiple ways for planets to fail at supporting life. Tidal forces add another layer of complexity. Because the planets orbit so close to their star and are likely tidally locked, one side permanently faces the star while the other side remains in eternal darkness. This creates extreme temperature gradients. The day side might be scorching hot while the night side freezes. Any atmosphere would constantly circulate, trying to redistribute heat from day to night. This circulation could create permanent storms, winds that never stop, weather patterns unlike anything Earth experiences. But tidal locking isn't necessarily bad for life. The twilight zones, the regions between permanent day and permanent night, could be remarkably stable. Temperatures there might remain moderate, avoiding the extremes of either hemisphere. If liquid water exists, it would likely pool in these twilight regions, creating narrow bands where conditions stay relatively constant. Life, if it exists, might be confined to these transitional zones, thriving in the permanent sunset of a tidally locked world. Scientists debate whether we could ever know for certain if these planets host life. Detecting an atmosphere is one thing. Proving that atmosphere contains biosignatures, gases produced by living organisms, is far more challenging. Oxygen is the classic example. On Earth, oxygen exists in our atmosphere because photosynthetic organisms constantly produce it. Without life, oxygen would quickly react with surface rocks and disappear. Finding oxygen in TRAPPIST-1E's atmosphere would be compelling evidence for life. But oxygen alone isn't enough. Geological processes can produce oxygen without life. We need combinations of gases, chemical signatures that only make sense if biology is present. Oxygen combined with methane, for instance, would be powerful evidence because these gases react with each other and shouldn't coexist unless something continuously produces them. Life produces both. Geology typically doesn't. The James Webb Space Telescope will spend years studying TRAPPIST-1. Each time a planet passes in front of the star, starlight filters through its atmosphere and reaches us carrying information about what gases exist there. By analyzing this light, scientists can identify atmospheric components. But the signals are faint. Detecting them requires hundreds of observations, patient accumulation of data, building up evidence piece by piece until a picture emerges. Recent observations of TRAPPIST-1b have been discouraging. The planet appears to have no substantial atmosphere. This doesn't doom the entire system, but it raises questions about how well any of these planets have retained their atmospheres. If the innermost planet lost its gases, what about the others? Are we searching for life in a system where stellar activity has already stripped away the very atmospheres we need to study? TRAPPIST-1c faces similar scrutiny. Early measurements suggested the possibility of a thick carbon dioxide atmosphere. Subsequent observations found no evidence for it. Either the atmosphere is incredibly thin or composed of gases we haven't detected yet. Or perhaps it simply doesn't exist. Each negative result narrows the possibilities but doesn't eliminate hope. We're still learning how to interpret these observations, still understanding the limitations of our instruments. The system's age compounds these uncertainties. TRAPPIST-1 is roughly 7.6 billion years old, significantly older than our solar system. That's billions of additional years for stellar flares to pummel planets, for atmospheres to erode, for conditions to change. But it's also billions more years for life to emerge, evolve, and potentially leave detectable traces. Age cuts both ways. What happens next depends on what we find. If TRAPPIST-1e has an atmosphere, the focus shifts to characterizing it completely. Scientists will search for water vapor, carbon dioxide, methane, oxygen, and dozens of other compounds. Each detection or non-detection refines our understanding of what kind of world exists there. If we find nothing, attention might shift to the outer planets where conditions could be less hostile despite receiving less stellar energy. Human nature drives us to find patterns, to imagine what these worlds look like, to picture oceans and mountains and alien skies. But we need to resist premature conclusions. TRAPPIST-1 might host life. It might be completely dead. It might fall somewhere in between, with environments capable of supporting life but currently empty through cosmic accident. The only way to know is through methodical observation, collecting evidence without rushing to judgment. The implications extend beyond 7 planets around a dim star. TRAPPIST-1 is common in the galaxy. Not this exact system, but ultra-cool dwarf stars with compact planetary systems. If we determine that TRAPPIST-1 planets can't support life, we're effectively ruling out billions of similar systems. If we find that life can exist there despite the challenges, we're opening up vast regions of the galaxy as potential habitats. Either answer reshapes our understanding of life's prevalence in the universe. Human outlined these possible outcomes. What actually exists at TRAPPIST-1 remains unknown. But each observation brings clarity, each measurement constrains possibilities. We're moving from speculation to data, from wondering to knowing. And the journey has barely started. The challenge isn't just detecting atmospheres. It's understanding what those atmospheres tell us about the planets beneath them. An atmosphere doesn't exist in isolation. It's shaped by volcanic activity, weathering of rocks, biological processes, and the relentless bombardment of stellar radiation. Consider what happens when starlight passes through a planetary atmosphere. Different molecules absorb specific wavelengths of light. Oxygen absorbs certain frequencies. Water vapor absorbs others. Methane has its own signature. By measuring which wavelengths are missing from the light that reaches us, scientists can deduce what gases are present. But this requires the planet to pass directly between us and its star, creating a transit. During those few hours when the geometry aligns, telescopes collect as much data as possible. Then the planet moves on, and we wait weeks or months for the next opportunity. The signal we're measuring is incredibly weak. Imagine trying to detect a single grain of sand added to a beach by measuring the beach's total weight. That's the scale we're working with. The atmosphere of an Earth-sized planet adds roughly 1 part in 10,000 to the total light blocked during a transit. Within that tiny signal, we're searching for even tinier variations caused by specific molecules. It's technically possible, but it requires perfect conditions, flawless calibration, and patience. TRAPPIST-1 doesn't make this easy. The star itself is variable, with surface features that change over time. Star spots, the cooler regions on a star's surface, can mimic or obscure atmospheric signals. When a planet transits across a star spot, the light curve changes in ways that have nothing to do with the planet's atmosphere. Separating these effects requires multiple observations and sophisticated modeling. We're essentially trying to subtract the star's natural variations to isolate the planet's contribution. The James Webb Space Telescope was designed for exactly this kind of work. Its infrared capabilities allow it to detect molecules that are invisible to optical telescopes. Carbon dioxide, for instance, has strong absorption features in the infrared. Water vapor shows up clearly. Methane becomes detectable. But even Webb has limitations. Observing a single planet requires multiple transits. Building up enough signal to confidently detect an atmosphere can take dozens of hours of telescope time. With 7 planets to study and limited observing windows, the process stretches across years. Early results from Webb have been humbling. The instrument works brilliantly, but the planets aren't cooperating. TRAPPIST-1b shows no sign of a thick atmosphere. TRAPPIST-1c remains ambiguous. These aren't instrument failures. They're real results telling us something important about how planets survive around red dwarf stars. Maybe atmospheres around these stars are rare. Maybe they exist but are composed of gases we haven't thought to look for. Or maybe we need more data before drawing conclusions. The habitable zone planets present a different puzzle. TRAPPIST-1e receives roughly the same amount of energy from its star as Earth receives from the Sun. If it has an atmosphere, that atmosphere could support liquid water on the surface. But the planet is tidally locked, with one side permanently facing the star and the other side in eternal darkness. This creates extreme temperature gradients. The day side could be scorching. The night side frozen. Only in the narrow band between them, the terminator region, might temperatures allow liquid water. Unless the atmosphere redistributes heat. A thick atmosphere with strong winds could transport warmth from the day side to the night side, moderating temperatures across the entire planet. Earth's atmosphere does this to some extent. Venus does it far more effectively, with winds so powerful they circle the planet in just 4 days despite the planet's slow rotation. If TRAPPIST-1e has similar atmospheric circulation, the entire surface could be habitable. But if the atmosphere is thin or non-existent, the terminator might be the only refuge. This matters for more than just temperature. Atmospheric circulation affects where water accumulates. On a tidally locked planet with poor heat transport, all the water could freeze on the night side, leaving the day side as a scorched desert. With good circulation, water could remain liquid across much of the surface. The difference between these scenarios determines whether the planet could support life, and whether that life might be detectable from Earth. Detecting life itself requires finding biosignatures, gases that are produced by living organisms and wouldn't persist in the atmosphere without continuous replenishment. Oxygen is the classic example. On Earth, photosynthetic organisms produce vast amounts of oxygen. Without them, oxygen would rapidly combine with rocks and disappear from the atmosphere. Finding oxygen around another planet doesn't guarantee life, but it strongly suggests biological activity. Methane is another candidate. On Earth, methane comes from both biological and geological sources. Bacteria in swamps produce methane. Volcanic activity releases it. Finding methane alone doesn't prove life exists. But finding methane and oxygen together creates a stronger case. These gases react with each other, so their simultaneous presence suggests something is actively producing them. Life is the most obvious explanation. The problem is false positives. Geological processes can produce oxygen under certain conditions. Photochemistry in the upper atmosphere can generate small amounts. Methane can accumulate if volcanic activity is high and chemical reactions are slow. We need multiple lines of evidence, combinations of gases that can't be easily explained by non-biological processes. And we need to understand the planet's geology, its star's activity, and its atmospheric chemistry well enough to rule out alternative explanations. TRAPPIST-1 stellar activity complicates biosignature detection. The star's flares produce ultraviolet radiation that can break apart atmospheric molecules, creating fragments that recombine in unexpected ways. This can generate false biosignatures, gases that look biological but are actually products of stellar radiation. Distinguishing between life and stellar chemistry requires understanding both processes in detail. The search extends beyond just looking for familiar gases. Life on Earth produces thousands of different compounds. Some, like dimethyl sulfide, are produced almost exclusively by marine organisms. Others, like certain chlorinated compounds, come from specific types of bacteria. These trace gases are harder to detect than oxygen or methane, but they're more specific. Finding them would provide stronger evidence for life. But it also requires knowing what to look for and having instruments sensitive enough to detect gases present at parts per billion. Computer models help predict what atmospheres around TRAPPIST-1 planets might look like under different conditions. Scientists simulate planets with various compositions, different amounts of volcanic activity, different ocean coverage, and different types of life. Each simulation produces a predicted spectrum, a pattern of light absorption that would result from that specific combination of conditions. By comparing observed spectra to these models, researchers narrow down which scenarios match reality. These models reveal surprising possibilities. A planet covered entirely by ocean might have an atmosphere dominated by water vapor and nitrogen. A volcanic world could have a thick carbon dioxide atmosphere with sulfur compounds. A planet with extensive forests might show strong oxygen signals alongside organic vapors. Each possibility requires different observational strategies and different interpretations of the data we collect. The outer planets, TRAPPIST-1F and G, orbit in the system's outer habitable zone. They receive less stellar energy, making them colder than the inner worlds. But cold doesn't mean lifeless. Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath icy crusts, maintained by tidal heating. TRAPPIST-1's outer planets might follow similar patterns, with frozen surfaces hiding liquid water oceans below. Life in these oceans wouldn't show up in atmospheric observations, but it could still exist. Detecting subsurface oceans requires different techniques. Scientists look for magnetic fields generated by conductive fluids moving through the planet's interior. They search for evidence of geological activity that might indicate internal heat. They measure how the planet's gravity changes as it orbits, which can reveal whether a liquid layer exists beneath the surface. These observations are harder to make than atmospheric studies, but they're possible with sufficiently powerful telescopes and patient observation. The timeline for answering these questions stretches far into the future. Webb will observe TRAPPIST-1 planets for years, accumulating data transit by transit. Future telescopes, currently in the planning stages, will build on this foundation. The extremely large telescope, under construction in Chile, will have a mirror 39 meters across, dwarfing any existing ground-based telescope. It could directly image planets around nearby stars and study their atmospheres with unprecedented detail. But it won't be operational until the 2030s. Meanwhile, the search continues with existing tools. Ground-based telescopes track the system constantly, measuring changes in stellar activity and refining our understanding of planetary orbits. Space telescopes like Hubble and Spitzer have contributed observations, though neither was optimized for this kind of work. Webb carries the immediate burden, producing results that will shape the next decade of research. What we learn at TRAPPIST-1 will influence how we approach thousands of other planetary systems. If red dwarf planets can maintain atmospheres despite stellar activity, it validates searching for life around the galaxy's most common stars. If they can't, our focus shifts to sun-like stars, which are rarer but potentially more hospitable. Either outcome provides crucial information, but one expands our search space while the other constrains it dramatically. The 7 worlds of TRAPPIST-1 aren't just interesting objects. They're test cases for planetary habitability, laboratories where we can study how planets form, devolve, and maintain conditions suitable for life. Each observation adds another piece to a puzzle that spans astronomy, geology, atmospheric science, and biology. And somewhere in that puzzle lies an answer to whether we're alone. The search for biosignatures at TRAPPIST-1 depends on understanding what counts as proof. Oxygen in an atmosphere sounds like clear evidence of life, but nature produces oxygen through non-biological processes too. Ultraviolet radiation can split water molecules, releasing hydrogen into space and leaving oxygen behind. Photochemistry in carbon dioxide-rich atmospheres can generate small amounts of oxygen. The presence of oxygen alone isn't enough. Scientists need to find combinations of gases that can't coexist without constant replenishment from biological activity. Methane and oxygen together create such a combination. In Earth's atmosphere, these two gases react with each other, destroying both within years. Yet both persist because life constantly produces them. Plants generate oxygen. Bacteria in wetlands and animal digestive systems produce methane. Without this continuous input, both gases would vanish. Finding them together on a distant planet would suggest something actively maintains that chemical imbalance. But even this signature has caveats. Volcanic activity produces methane. Subsurface chemical reactions can release it. The ratio matters. The concentrations matter. The presence of other gases that might explain the pattern matters. A complete biosignature profile requires multiple lines of evidence converging on the same conclusion. No single measurement proves life exists. Only patterns that become progressively harder to explain through geology alone build a convincing case. Water vapor presents another layer of complexity. Every habitable planet should have water in its atmosphere, but how much? Too little suggests a dry world with limited liquid water on the surface. Too much might indicate a runaway greenhouse effect, where oceans evaporate and the planet becomes Venus-like. The amount of water vapor, its distribution through the atmosphere, and how it changes with planetary seasons all provide clues about surface conditions. Clouds complicate everything. They block light, making it harder to analyze atmospheric composition beneath them. They reflect starlight, changing how bright the planet appears during transit. They form at different altitudes depending on temperature and pressure, creating layers that absorb different wavelengths. A planet with permanent cloud cover might hide its most interesting features. Scientists develop techniques to peer through clouds, using wavelengths less affected by water droplets or ice crystals, but every cloud layer reduces the quality of data collected. TRAPPIST-1's variability adds another challenge. The star dims and brightens as dark spots rotate across its surface. It produces flares that temporarily increase its brightness. These changes affect how much light reaches each planet and how that light interacts with planetary atmospheres. When the star flares, it pumps extra energy into the upper atmosphere, potentially driving chemical reactions that wouldn't normally occur. To identify biosignatures, scientists must separate signals caused by stellar activity from signals caused by planetary processes. This requires observing the system repeatedly over months and years. A single transit shows what the atmosphere looks like at one moment. Multiple transits reveal patterns. Does the atmospheric composition change with seasons? Does it respond to stellar flares in predictable ways? Does it remain stable over time, suggesting established cycles rather than temporary events? Only long-term monitoring answers these questions. The inner planets, especially TRAPPIST-1b and c, face the harshest conditions. They orbit so close that stellar radiation strips away their atmospheres over geological timescales. Computer models show that planets this close to active red dwarfs lose massive amounts of atmosphere, potentially evaporating entire oceans worth of water into space. Yet these planets might retain thick atmospheres if they started with enough volatile material. Or they might be airless rocks, stripped bare billions of years ago. Webb's first observations of TRAPPIST-1b suggested minimal atmosphere, but the data wasn't conclusive. The planet absorbed light consistent with bare rock, but certain atmospheric compositions could produce similar results. Carbon dioxide-rich atmospheres without clouds might appear nearly identical to no atmosphere at all. Distinguishing between these scenarios requires additional observations at different wavelengths, building a complete picture of what light the planet absorbs and reflects. TRAPPIST-1c showed slightly more promise. Observations hinted at possible atmospheric features, though again, the data remained ambiguous. The challenge with these inner planets isn't just detecting atmospheres. It's determining whether any detected atmosphere is primordial, left over from the planet's formation, or secondary, produced by volcanic outgassing after the primordial atmosphere was lost. A secondary atmosphere would indicate ongoing geological activity, which requires internal heat. Internal heat suggests a molten core, which could generate magnetic fields, which might protect against stellar radiation. The middle planets, TRAPPIST-1d, E, and F, occupy the sweet spot where temperatures could allow liquid water. Computer models place them in or near the habitable zone, but models depend on assumptions. How reflective is the surface? How much greenhouse warming occurs? What's the atmospheric composition? Small changes in these parameters shift the habitable zone boundary significantly. A planet right at the edge might be habitable or frozen depending on factors we haven't measured yet. TRAPPIST-1e draws particular attention because it receives stellar energy similar to what Earth receives from the Sun. Its size and density closely match Earth's. Its orbital period of 6 days means it's tidally locked, with one side permanently facing the star and the other in eternal darkness. This creates extreme temperature gradients that drive powerful atmospheric circulation. Air heated on the day side rises and flows toward the night side, where it cools and sinks, creating planet-wide wind patterns unlike anything Earth experiences. These winds might actually help maintain habitable conditions. They transport heat from the scorched day side to the frozen night side, moderating temperatures across the planet. Without this heat redistribution, the day side might be too hot for liquid water while the night side freezes solid. But with strong enough winds, a band of moderate temperature could exist between the two extremes, possibly sustaining liquid water in a ring around the terminator, the boundary between day and night. Testing this hypothesis requires measuring how temperature varies across the planet's surface. As TRAPPIST-1e orbits, different parts of its surface face Earth. By observing how much infrared light the planet emits during different parts of its orbit, scientists can map temperature variations. A planet with strong heat redistribution shows less temperature variation than one without. These observations are challenging because the planet is small and the temperature difference is subtle, but Webb's infrared instruments are designed precisely for this work. Tidal locking also affects magnetic fields. Earth's magnetic field comes from its rotating molten core. TRAPPIST-1e doesn't rotate relative to its star, though it does rotate once per orbit relative to the rest of the universe. Whether this slower rotation can sustain a magnetic field remains uncertain. Some models suggest yes, others no. Without a magnetic field, stellar wind and radiation could strip the atmosphere over time. Detecting or ruling out magnetic fields on exoplanets requires observing how stellar wind interacts with the planet, looking for signatures of deflection that would indicate a protective magnetic bubble. The possibility of moons adds another variable. Earth's moon stabilizes our planet's axial tilt, preventing wild climate swings. It drives tides that might have been important for the origin of life. TRAPPIST-1's planets could have moons, though detecting them is nearly impossible with current technology. A large moon would affect the planet's orbit in measurable ways, creating tiny variations in transit timing that repeat with the moon's orbital period. Searching for these signals requires years of precise observations and sophisticated data analysis. Water worlds represent another scenario that might exist at TRAPPIST-1. If a planet formed farther from the star and migrated inward, it might have started as an icy body that melted as it entered warmer regions. The result would be a planet with global oceans potentially hundreds of kilometers deep, with no exposed land. Such planets might be common around red dwarfs, and they present unique habitability questions. Deep oceans with no seafloor contact limit the availability of nutrients. On Earth, life depends on cycles that involve both land and sea. Minerals weather from rocks, wash into oceans, and feed marine ecosystems. A water world lacks this cycle. Life might still exist near hydrothermal vents on the ocean floor, similar to Earth's deep-sea ecosystems, but it would face constraints. Whether complex life could evolve under these conditions remains speculative. High-pressure ice adds another twist. At sufficient depth, water pressure becomes so intense that water molecules form exotic ice structures that remain solid despite warm temperatures. A water world might have a liquid ocean layer sitting atop a thick shell of high-pressure ice, which itself rests on a rocky core. This creates isolated environments. Life in the upper ocean couldn't access nutrients from the core. Life near the core couldn't access energy from the star. Understanding whether such planets exist at TRAPPIST-1 requires measuring their densities precisely and modeling their internal structures. The outermost planet, TRAPPIST-1H, remains the least studied. It orbits every 20 days, making transits rare. Less data means less certainty about its properties. It might be a frozen world, or it might receive enough tidal heating from gravitational interactions with other planets to maintain subsurface liquid. Each observation slowly fills in details, but years of work remain before we understand this distant member of the system. The search for life doesn't stop at finding water or oxygen. Those are starting points, not conclusions. Life leaves traces beyond basic chemistry. On Earth, organisms have transformed the planet's surface in ways detectable from space. Forests change reflectivity. Phytoplankton alter ocean color. Seasonal cycles create patterns. Cities glow at night. Finding life on TRAPPIST-1's planets won't come from a single measurement, but from accumulating evidence that something beyond geology and chemistry is happening. Biosignatures fall into categories. Atmospheric biosignatures involve gases that shouldn't persist without constant replenishment. Oxygen is one example, but it's not the only one. Methane in the presence of oxygen is intriguing because these gases react and destroy each other on geological timescales. Finding both together suggests something continuously produces them. On Earth, that something is life. Microbes produce methane. Plants produce oxygen. Together they create an atmospheric imbalance. Surface biosignatures involve changes visible when observing the planet's surface. Vegetation reflects infrared light differently than bare rock or water. This creates a signature called the red edge, named for the sharp increase in reflectivity at specific wavelengths. Detecting this requires observing the planet as it rotates, watching how light changes as different regions face the observer. Seasonal biosignatures involve patterns that repeat with the planet's orbit. If TRAPPIST-1e has seasons, vegetation might grow and recede, changing the planet's appearance. Monitoring this requires observations spread across multiple orbits, watching for repeated patterns that match environmental cycles. But every biosignature has false positives. Oxygen can come from water molecules breaking apart under ultraviolet light. Methane seeps from geological processes. Surface changes might be dust storms or ice formation. Seasonal patterns could be atmospheric circulation. The challenge is distinguishing biology from everything else. This requires multiple independent measurements. If oxygen appears alongside other gases in unusual ratios, if surface features change in ways consistent with growth rather than weather, if patterns persist across years in stable configurations, the case for life strengthens. No single observation proves anything. The weight of evidence accumulates. Technosignatures represent another approach. Rather than searching for life's chemical traces, we look for technology. Radio signals, laser pulses, atmospheric pollution from industrial processes, structures large enough to see from interstellar distances. This assumes life not only exists but has developed technology. That's a much stronger assumption than looking for microbes, but it has advantages. Technology produces signals far stronger than biology. A radio transmitter can outshine a star at specific frequencies. Industrial pollution creates atmospheric signatures unlike anything natural. The challenge is knowing where to look and what to look for. TRAPPIST-1's proximity makes it an obvious target. The Breakthrough Listen initiative has already scanned these planets for radio signals. So far, nothing. But absence of evidence isn't evidence of absence. Maybe they don't use radio. Maybe they do, but we haven't listened at the right time or frequency. Maybe technology is rare. Maybe it's common, but civilizations don't last long enough to overlap with our listening period. Contamination concerns work both ways. When humans eventually send probes to other star systems, we risk contaminating those worlds with Earth life. Hardy microbes could survive spaceflight. If they reach a habitable planet, they might multiply, potentially destroying or altering native ecosystems before we even know those ecosystems exist. Planetary protection protocols exist to prevent this, but they're designed for solar system exploration. Interstellar missions face different challenges. Travel times span decades or centuries. Sterilization must last that long. We also worry about contaminating our own measurements. If we send a probe that lands on TRAPPIST-1 and later detects organic molecules, how do we know those molecules weren't brought from Earth? Future missions will require extreme care in design, construction, and operation to ensure any discoveries are real. Time introduces profound complications. TRAPPIST-1's light takes 40 years to reach us. When we observe these planets, we see them as they were 4 decades ago. If we detect a biosignature today, it represents life that existed when humanity had just begun studying exoplanets. If we send a signal and receive a reply, nearly a century passes. This delay affects how we plan observations and interpret results. It also raises philosophical questions. What if life existed but went extinct? What if it's about to emerge but hasn't yet? We're looking at a snapshot, not a live feed. Everything we learn is historical. The TRAPPIST-1 system's age matters too. The star is roughly 8 billion years old, nearly twice the Sun's age. Life on Earth appeared within the first billion years after the planet formed. If the same happened at TRAPPIST-1, life there has had billions of years longer to evolve. This cuts both ways. More time means more opportunity for life to arise, adapt, and diversify. But it also means more time for catastrophes. Asteroid impacts, stellar flares, atmospheric loss, any number of events could have wiped life out multiple times. Ancient systems might be graveyards. Or they might host biospheres far more complex than Earth's, with ecosystems that ever find themselves across eons of selection and adaptation. Comparing timelines between systems reveals how contingent everything is. Earth's history includes 5 major mass extinctions, countless minor ones, and several near-total sterilizations. Each reset evolution's progress. If TRAPPIST-1's planets experienced fewer catastrophes, life might be more advanced. If they experienced more, it might be simpler or absent. We have no way to predict this without observing. The Fermi paradox looms over all discussions of life beyond Earth. If planets are common and life arises readily, where is everyone? Why don't we see evidence of civilizations? TRAPPIST-1 offers a test case. If we search thoroughly and find nothing, that tells us something about how rare or fragile complex life is. If we find microbes but no technology, that suggests biological life is common but technological civilizations are rare. If we find both, it challenges our assumptions about how often intelligence emerges. Observation strategies continue evolving. Early work focused on basic planet detection and characterization. Current efforts target atmospheric composition. Future missions will map surfaces, search for seasonal changes, and monitor long-term atmospheric stability. Each generation of instruments reveals new details. Webb's observations will continue for years, building datasets that allow comparison across seasons and orbits. Ground-based telescopes, especially the upcoming extremely large telescopes, will complement space observations. These giant instruments, with mirrors 30 to 40 meters across, can detect faint atmospheric signals Webb might miss. They'll also observe at different wavelengths, providing independent measurements. Direct imaging remains a distant goal. Current instruments can't separate a planet's light from its star's glare except in rare cases involving young, hot planets orbiting far from bright stars. TRAPPIST-1's planets are too close and too cool for this technique. But future technologies might succeed. A space telescope equipped with a star shade, a precisely positioned screen that blocks starlight while allowing planet light through, could image these worlds directly. This would reveal surface features, cloud patterns, and possibly even continents and oceans. Such missions are being designed now but won't launch for decades. When they do, TRAPPIST-1 will be among the first targets. Sample return missions, though far beyond current capability, represent the ultimate goal. A probe that travels to TRAPPIST-1, lands on a planet, collects samples, and returns to Earth would answer questions no remote observation can. It would take centuries with current propulsion technology. Faster systems are theoretical. Breakthrough Starshot proposes using powerful lasers to accelerate tiny probes to 20% of light speed, reducing travel time to 40 years. These probes couldn't slow down or return, but they could transmit data during a brief flyby. Even this ambitious concept faces enormous engineering challenges. Whether it's practical remains uncertain. Regardless of technical hurdles, the scientific motivation is clear. TRAPPIST-1 offers the best near-term opportunity to answer whether life exists beyond Earth. The discovery of this system changed how we think about planetary systems. Before TRAPPIST-1, we knew planets could orbit red dwarfs, but we didn't expect systems this compact or this rich. Its existence suggests similar systems are common. Thousands of red dwarfs lie within 100 light-years. If even a fraction host planet systems like TRAPPIST-1, nearby habitable worlds might number in the hundreds. This changes the scale of the search. We're not looking for rare exceptions but for common outcomes of planet formation. The question shifts from whether habitable planets exist to which ones host life. Cultural impact extends beyond science. TRAPPIST-1 appears in fiction, art, and public imagination as a symbol of possibility. It represents a place we can almost touch, close enough that future generations might visit, real enough that we can study it seriously. Unlike vague discussions of life in the universe, TRAPPIST-1 is specific. It has coordinates. It has planets with names. It has properties we can measure. This concreteness makes the search for life feel tangible rather than abstract. When we ask whether life exists elsewhere, we can point to an actual place and say, we're checking there. The answer matters not just scientifically but philosophically. Finding life would confirm we're not alone. Finding nothing would raise questions about how rare life is and whether intelligence is a cosmic accident. Either way, the search itself transforms us. The process of looking forces us to confront assumptions about life's requirements, challenges our understanding of habitability, and tests the limits of our technology. Every observation teaches us something new, whether or not we find what we're searching for. The data we collect today forms the foundation for discoveries decades from now. Results from Webb's observations won't arrive in a single dramatic announcement. Science rarely works that way. Instead, papers will appear describing atmospheric compositions, temperature structures, and chemical inventories. These technical reports will gradually build a picture of what these worlds are actually like. Some findings will exclude certain possibilities. If a planet shows no water vapor, we'll know its surface is dry. If another shows abundant methane without oxygen, we'll know it's not Earth-like. Negative results matter as much as positive ones. They narrow the search space and guide future observations. Other findings will open new questions. Detecting unexpected molecules might indicate processes we don't understand. Seeing atmospheric patterns that change with time could reveal weather systems or seasonal cycles. Each answer generates new questions, pushing the investigation deeper. The real challenge lies in interpretation. Atmospheric chemistry is complex. The same molecule can form through biological or geological processes. Oxygen, often considered a biosignature, can be produced without life through water vapor dissociation if ultraviolet radiation is strong enough. Methane can emerge from volcanic activity or serpentinization, a chemical reaction between water and certain rocks. Distinguishing between these scenarios requires careful modeling and multiple lines of evidence. Context matters enormously. A small amount of oxygen might be geological noise. Large amounts combined with methane would be harder to explain without life. Phosphine, a molecule that breaks down quickly, would be especially interesting because it needs constant replenishment. On Earth, life produces it. Whether geological processes can generate significant quantities remains debated. Finding it on TRAPPIST-1 would trigger intense scrutiny and follow-up observations. Temperature measurements provide crucial context for interpreting chemistry. If a planet's surface is too hot, water can't remain liquid. If it's too cold, life as we know it can't function. Webb can estimate surface temperatures by measuring thermal emission, the infrared glow objects emit based on their heat. Comparing these temperatures to models tells us weather conditions allow liquid water. Clouds complicate this analysis. They reflect starlight and trap heat, altering surface temperatures in ways that depend on their altitude, composition, and coverage. Thick cloud decks might make a planet's surface warmer than expected, while high-thin clouds could cool it. Detecting clouds requires observing how a planet's brightness changes at different wavelengths. Water clouds scatter blue light more than red. Sulfuric acid clouds behave differently. By measuring these spectral signatures, we can infer cloud properties. This matters because clouds affect habitability. Too much cloud cover blocks starlight, reducing photosynthesis. Too little allows harmful radiation to reach the surface. The right amount creates a stable climate. Magnetic fields play a role we can't yet measure directly but must infer. A planet's magnetic field shields its atmosphere from stellar wind, streams of charged particles that erode atmospheres over time. Earth's magnetic field protects our atmosphere. Mars lost most of its atmosphere because it lacks a strong field. Red dwarfs produce powerful flares that accelerate atmospheric loss. Without magnetic protection, even a planet in the habitable zone might lose its atmosphere within hundreds of millions of years. Whether TRAPPIST-1's planets have magnetic fields depends on their internal structure. Planetary magnetic fields are generated by liquid metal cores churning through convection. This requires a planet to be large enough to stay geologically active and have the right composition. TRAPPIST-1 and F might meet these criteria. The others might not. Tidal heating, caused by gravitational squeezing as planets orbit, could keep interiors molten even if they'd otherwise cool. This might generate magnetic fields where they wouldn't normally exist. We won't know until we develop techniques to detect planetary magnetic fields remotely. One proposed method involves measuring how stellar wind particles interact with a planet's magnetosphere, creating radio emissions we could detect. This technology doesn't exist yet but could emerge within decades. Tidal locking introduces unique challenges and opportunities. If these planets always show the same face to their star, they experience permanent day on one side and permanent night on the other. Heat distribution becomes critical. Without efficient atmospheric circulation, the day side could be too hot while the night side freezes solid. Water would evaporate on one side and condense as ice on the other, eventually leaving the planet dry. But if the atmosphere is thick enough, winds could transport heat from day to night, creating a habitable twilight zone between extremes. This band, where temperatures remain moderate, might be the most favorable region for life. Ocean worlds would handle tidal locking differently. Water's high heat capacity allows it to store and transport thermal energy efficiently. Global oceans could circulate heat around the planet, preventing extreme temperature differences. This makes ocean worlds potentially more stable than rocky planets with thin atmospheres. Whether TRAPPIST-1's planets have global oceans depends on their formation history and subsequent evolution. If they formed beyond the snow line and migrated inward, they might have started water-rich. Subsequent atmospheric loss and surface processes would determine how much water remains today. Geological activity offers another piece of the habitability puzzle. Active geology recycles nutrients, releases gases that replenish atmospheres, and creates diverse environments. Volcanism on Earth releases carbon dioxide, which regulates climate over geological timescales. Without volcanism, carbon dioxide gets locked in rocks and the greenhouse effect weakens, eventually making the planet too cold. Plate tectonics, Earth's system of moving crustal plates, drives this recycling. Whether small planets can maintain plate tectonics is uncertain. Earth might be near the lower size limit for this process. TRAPPIST-1's planets, being slightly smaller, might not have plate tectonics. But they could have other forms of geological activity. Stagnant lid tectonics, where a single rigid crust covers a convecting interior, could still drive volcanism. Tidal heating from gravitational interactions with neighboring planets could provide additional energy for geological processes. This might keep smaller planets active longer than they'd otherwise remain. Biosignatures fall into several categories. Gas phase biosignatures are molecules in the atmosphere that life produces. Oxygen, methane, and phosphine are examples. Surface biosignatures are features visible on a planet's surface that indicate life, such as vegetation's distinctive reflectance spectrum. Temporal biosignatures are changes over time that suggest biological cycles, like seasonal variations in atmospheric composition. Each type requires different observation techniques. Gas phase biosignatures are most accessible now because we can study them through transit spectroscopy. Surface biosignatures need direct imaging, which isn't yet possible for these planets. Temporal biosignatures require long-term monitoring, observing the same planet repeatedly over months or years to detect changes. Webb can provide some temporal coverage, but dedicated missions would do better. False positives remain a serious concern. A false positive occurs when we detect something that looks like a biosignature but actually has a non-biological origin. This could mislead us into announcing the discovery of life when none exists. The scientific community would require extraordinary evidence before making such a claim. Multiple independent observations, thorough modeling to rule out non-biological explanations, and peer review by experts would all be necessary. Even then, uncertainty would remain until we could study the planet more directly. False negatives are equally important. A false negative happens when life exists but we fail to detect it. This could occur if life uses biochemistry different from Earth's, producing molecules we don't recognize as biosignatures. It could also happen if life exists but doesn't produce detectable atmospheric signatures, perhaps because it's confined to subsurface oceans or exists in small quantities. We might miss life simply because we're not looking in the right way. The possibility of non-Earth-like life expands the search dramatically. All our biosignature concepts are based on Earth life, which uses carbon-based chemistry, liquid water, and specific metabolic pathways. Life elsewhere might work differently. Silicon-based biochemistry, liquid methane as a solvent, or completely different metabolic processes could exist. We wouldn't recognize these as biosignatures because we don't know what to look for. This limitation means our search is biased toward finding life like ours. We might fly right past evidence of alien life without recognizing it. Addressing this requires creativity and open-mindedness. Some researchers propose looking for disequilibrium rather than specific molecules. Disequilibrium occurs when atmospheric chemistry is out of balance, with reactive gases coexisting when they should react and disappear. On Earth, oxygen and methane shouldn't coexist because they react chemically. They do because life constantly produces both. Detecting similar disequilibria elsewhere might indicate life even if the specific molecules differ from Earth's biosignatures. Artificial intelligence and machine learning are being applied to biosignature detection. These algorithms can analyze vast datasets, identifying patterns humans might miss. They can also model thousands of possible atmospheric compositions, helping distinguish biological from geological signatures. Training these systems requires careful work. They learn from examples, so if we only show them Earth-like biosignatures, they'll only recognize those. Expanding their training to include hypothetical non-Earth biochemistries improves their flexibility. As these tools mature, they'll become essential for processing the enormous amounts of data future telescopes will collect. Human intuition and machine analysis will work together, each compensating for the other's weaknesses. The timeline for answers stretches across decades. Webb's observations will continue for years, gradually building a comprehensive picture of TRAPPIST-1's planets. Follow-up missions will launch in the 2030s and 2040s, each more capable than the last. By mid-century, we might have definitive answers about whether these worlds host life. Or we might find the question is more subtle than we expected, requiring even more sophisticated observations. Either outcome advances our understanding. The search for life around TRAPPIST-1 sits within a broader revolution in how we understand planets and their potential for habitability. 50 years ago, we knew of no planets beyond our solar system. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. This explosion of discovery fundamentally changed our perspective. Planets aren't rare cosmic accidents. They're the natural outcome of star formation, appearing around most stars we examine closely enough. Rocky planets in particular seem common, suggesting the raw materials for life are widespread throughout the galaxy. TRAPPIST-1's system represents something special within this abundance. Most exoplanets we've found orbit much hotter stars than TRAPPIST-1. Hot stars age quickly and emit intense radiation that can strip planetary atmospheres. They also produce more ultraviolet light, which damages biological molecules. TRAPPIST-1's cool, stable nature provides a gentler environment. Its planets won't face the radiation bombardment that plagues worlds around hotter stars. The star will shine for trillions of years, far longer than our sun's remaining lifespan. If life needs time to evolve complexity, TRAPPIST-1 offers nearly unlimited patience. The system's architecture also matters. Having 7 planets packed so closely creates gravitational interactions that could prove beneficial. Tidal forces from neighboring planets might generate internal heating, keeping subsurface oceans liquid even on worlds that receive little starlight. This expands the habitable zone beyond simple calculations based on surface temperature. A planet might look too cold to support life when considering stellar radiation alone, yet maintain liquid water underground through tidal heating. Europa and Enceladus in our solar system demonstrate this principle. Both moons orbit far from the Sun where surface temperatures plunge below -100 degrees Celsius, yet both harbor subsurface oceans kept liquid by tidal flexing. TRAPPIST-1's planets might experience similar conditions, creating multiple environments where life could emerge and persist. Understanding these worlds requires thinking beyond Earth-based assumptions. Our planet's history shapes how we imagine habitability. We picture continents and oceans, a nitrogen-oxygen atmosphere, and a protective magnetic field. But these features aren't universal requirements. Venus-like worlds with crushing atmospheric pressure and sulfuric acid clouds seem hostile, yet life adapted to those conditions would thrive. Ocean worlds with no land whatsoever could support rich biospheres beneath kilometers of water. Planets with thin atmospheres and low gravity might develop life in underground caves where conditions remain stable. The challenge lies in recognizing life signatures when they emerge from these alien contexts. We're building a library of possibilities, modeling how different planetary conditions produce different atmospheric chemistries. This library will help interpret observations when we finally collect them. If we detect an atmosphere that doesn't match any known geological process but fits a biological model, we'll have found something significant. The strength of that claim depends on how thoroughly we've ruled out alternatives. Geology can mimic biology in frustrating ways. Volcanic outgassing produces many of the same molecules life creates. Lightning can generate complex organic compounds without any biological involvement. Photochemistry driven by stellar ultraviolet light creates chemical reactions that might look like metabolism. Distinguishing true biosignatures from these false positives requires detailed modeling and multiple lines of evidence. No single observation will suffice. We need patterns, consistency across different measurements, and explanations that make sense given what we know about the planet's geology and atmospheric physics. The scientific method demands skepticism. When we think we've found something extraordinary, we must work harder to disprove it than to confirm it. This approach frustrates those who want quick answers, but it protects against embarrassment and ensures that when we do announce a discovery, it stands on solid ground. The search for life around TRAPPIST-1 will proceed with appropriate caution. Future missions will expand our capabilities dramatically. Concepts under development include star shades, massive spacecraft that fly in formation with telescopes, blocking starlight to reveal faint planets more clearly. Interferometry, combining light from multiple telescopes to create a virtual instrument larger than any single telescope could be, will provide unprecedented resolution. Direct imaging missions could photograph TRAPPIST-1's planets as distinct points of light rather than inferring their properties indirectly. Each technological advance brings us closer to definitive answers. Ground-based telescopes continue improving as well. Extremely large telescopes currently under construction will have mirrors 30 meters across, dwarfing today's largest instruments. Adaptive optics systems correct for atmospheric distortion in real time, sharpening images to approach theoretical limits. These facilities will contribute to TRAPPIST-1 studies, particularly for longer-term monitoring and follow-up observations of interesting findings from space telescopes. The combination of space and ground-based observations creates a comprehensive picture. Space telescopes avoid atmospheric interference but have limited lifespans and can't be easily upgraded. Ground-based telescopes can be maintained and improved indefinitely but must contend with Earth's atmosphere. Using both together compensates for each approach's limitations. We're entering an era where planetary characterization becomes routine rather than exceptional. TRAPPIST-1 won't be studied in isolation but as part of a broader sample of potentially habitable worlds. Comparative planetology, examining many similar worlds to understand common patterns and unique variations, will reveal which planetary characteristics matter most for habitability. Does magnetic field strength correlate with atmospheric retention? Do planets with active plate tectonics develop more complex biosignatures? Does the presence of a large moon stabilize climate in ways that benefit life? These questions require large samples. TRAPPIST-1 provides 7 data points in a single system, making it invaluable for testing hypotheses about planetary habitability. Public interest in these discoveries remains intense. Each announcement about TRAPPIST-1 generates global attention. This enthusiasm reflects humanity's deep curiosity about our place in the universe. Are we alone? The question resonates across cultures and throughout history. Modern science finally has tools to answer it. The results will reshape philosophy, religion, and our understanding of life's significance. Finding life elsewhere, even simple microbial life, would demonstrate that biology emerges readily when conditions permit. This would suggest the universe teems with life, most of it probably simple, but some fraction potentially complex or even intelligent. Not finding life would also teach us something important. If we examine dozens of seemingly habitable worlds and detect no biosignatures, we'd need to reconsider our assumptions. Perhaps life requires conditions rarer than we thought. Perhaps the transition from chemistry to biology involves improbable steps. Perhaps life emerges commonly but rarely persists long enough to produce detectable signatures. Each null result narrows the range of possibilities, guiding future searches toward more promising targets. The TRAPPIST-1 system will remain a focus of astrobiology for generations. Its proximity, the number of potentially habitable planets, and the relatively easy observing conditions make it an ideal laboratory for testing our methods and assumptions. Whatever we learn there will inform searches around other stars, building a framework for understanding planetary habitability across the galaxy. This knowledge serves practical purposes beyond satisfying curiosity. As we contemplate humanity's long-term future, the question of where else we might live becomes increasingly relevant. Understanding which worlds could support life helps identify potential destinations for future exploration or even colonization. These considerations remain distant, but they motivate current research. We study TRAPPIST-1 not just to find life elsewhere but to understand life's requirements and possibilities. This understanding might one day help us recognize or even create habitable conditions on worlds that initially seem barren. The line between studying exoplanets and studying Earth blurs as we realize the same principles govern both. Atmospheric chemistry, climate dynamics, and the interplay between geology and biology operate by universal physical laws. Insights gained from examining TRAPPIST-1 improve our understanding of our own planet's history and future. Climate science benefits particularly from exoplanet research. Studying worlds with different atmospheric compositions, stellar inputs, and planetary characteristics tests our climate models under extreme conditions. If our models accurately predict TRAPPIST-1's atmospheric behavior, we gain confidence in their predictions for Earth's changing climate. The exchange flows both ways. Our detailed knowledge of Earth's atmosphere and biosphere informs how we interpret observations of distant worlds. 40 light-years now feels simultaneously vast and intimate. Vast because even traveling at unrealistic speeds, reaching TRAPPIST-1 would take centuries. Intimate because we can study its planets in detail, watching their atmospheres change with seasons, measuring their compositions, and searching for signs of life. Technology has collapsed the observational distance even as the physical distance remains unbridgeable with current capabilities. We've become neighbors with TRAPPIST-1 in a way that would astonish astronomers from just decades ago. Their wildest dreams about characterizing distant worlds have become our routine observations. The next generation of instruments will push boundaries we can barely imagine today. What seems impossible now might become straightforward in 20 years. The pace of discovery accelerates as technology and understanding advance together. TRAPPIST-1's secrets will gradually yield to our persistent questioning, revealing whether those distant worlds harbor the universe's most profound mystery or remain silent, waiting for life to arrive from elsewhere. The answer matters less than the journey itself. We stand at a threshold previous generations could only imagine. 7 worlds orbit a dim star close enough to study yet far enough to remain mysterious. Whether they harbor life or stand barren, whether their atmospheres persist or have vanished, whether oceans cover their surfaces or ice locks their water away, each discovery reshapes what we know about planets, habitability, and our own existence. TRAPPIST-1 represents more than coordinates in space. It's a mirror reflecting our assumptions back at us, forcing us to confront what we think we know about life's requirements. Every observation challenges conventional thinking. Every measurement refines theories built on studying a single example, Earth. We're learning that planets don't follow simple rules, that habitability isn't binary, and that nature experiments with configurations we never anticipated. The telescopes currently pointed at this system will continue their work for years. Data accumulates slowly, each transit adding fragments to an incomplete picture. Future instruments will fill gaps, answer questions the current generation of telescopes can't address, and pose new mysteries we haven't yet imagined. The process feels frustratingly slow measured against human lifespans, but it's remarkably fast compared to the billions of years these worlds have existed. What we find at TRAPPIST-1 will influence how we search elsewhere. If red dwarf planets retain atmospheres despite stellar violence, thousands of nearby systems become prime targets. If they don't, our focus shifts to rarer, sun-like stars. Either way, we gain knowledge that directs future efforts and resources. The search expands or contracts based on what these 7 planets reveal about planetary survival around the galaxy's most common stellar type. Somewhere in the accumulated observations, patterns will emerge. Atmospheric compositions that make sense given the planet's histories. Temperature distributions that reveal how energy moves through alien air. Chemical signatures that either suggest biology or don't. The absence of life matters as much as its presence. Both outcomes advance understanding. Both guide the next phase of exploration. We're no longer wondering whether other worlds exist. We're studying specific places, measuring their properties, and determining whether they could host life. This shift from philosophical speculation to empirical investigation represents one of science's great transitions. The question of whether we're alone moves from metaphysics to physics, from belief to data, from wondering to knowing. TRAPPIST-1's planets won't yield their secrets quickly or easily. They'll make us work for every answer, forcing us to build better instruments, develop more sophisticated models, and think more carefully about what constitutes evidence. This struggle drives progress. The harder the question, the more we learn in pursuing it. 40 light-years away, 7 worlds orbit a star that will outlive our sun by trillions of years. They've existed for billions of years already. They'll continue existing long after human civilization has transformed or disappeared. Right now, in this brief window of time, we're looking at them. We're measuring them. We're learning what they are and what they might become. The universe doesn't care whether we find life elsewhere. Planets orbit stars according to gravity's laws regardless of what we discover or conclude. But we care. The question drives us to build telescopes, launch missions, and spend decades analyzing data. It pushes our technology and understanding forward. And eventually, we'll know. Not through revelation or assumption, but through patient observation and careful analysis. TRAPPIST-1 will tell us its story. We just have to listen long enough to hear it.